All right, so let's get started. So like we said, we're going to start this class period where we ended last time with that example of our electrophilic addition to our conjugated dienes. Remember, because we have our conjugated diene, we could actually get two different products. Our 1,2 adduct, which is where we have our normal addition to one of those double bonds, but then we could also have this 1,4 adduct. That's a result of the resonance of that intermediate carbocation. And so where we left off was with this example where we were using this asymmetric conjugated diene. And we wanted to know what the major product was at high temperatures. And remember, at high temperatures, you're always just going to get whichever product is the most stable, regardless of whether it's 1,2 or 1,4. So we have to draw all four possible products. All right, so I'm going to draw my four possible products here. First, I'm going to pay attention to this double bond. All right, I'm going to do my products if this double bond was playing the role of the nucleophile. So my 1,2 adduct would be where my hydrogen is bound to carbon 1, bound to that first carbon. And my halogen, in this case it was HCl, so chlorine, is bound to that allylic carbon. All right, my 1,4 adduct that I would get if that double bond was playing the role of the nucleophile, I would see my double bond has moved as a result of that resonance. And so I have my hydrogen on carbon 1, but now my chlorine is over here on carbon 4. All right, so this would be the 1,2 adduct and the 1,4 adduct if this double bond was playing the role of the nucleophile. If instead my other double bond had been playing the role of the nucleophile, then my 1,2 adduct would have my hydrogen on that first carbon, and again my chlorine always in that allylic position. All right, if I was going to do the 1,4 adduct, again my hydrogen is on carbon 1, but now my double bond has moved positions because of resonance to be between carbons 2 and 3, and my chlorine is over here on the other end on carbon 4. All right, so this would now be the 1,2 adduct and the 1,4 adduct if this double bond was playing the role of the nucleophile. All right, if you're having trouble seeing where I got these products from, you want to convince yourself by drawing that reaction mechanism. All right, we talked about our reaction mechanisms for these electrophilic addition reactions. If you did your reaction mechanism starting with this double bond as your nucleophile, you would see how I got my 1,2 product, and then through resonance how I got my 1,4 product. And likewise, if you did your mechanism with this double bond starting as the nucleophile, you would see how I got my two products here. But the question is, which one of these is the major product at high temperatures? And what is it that we're looking for our major product at high temperatures? All right, so for example, in our previous problem, we said that at high temperatures, this was our major product. And that's because it's lower energy than the other one. How do we know it was lower energy? What were we looking at? Yeah, whichever one is the more substituted alkene. More substituted means more stable. If I look, this one's a mono-substituted, and this one's a di-substituted. So more substituted means more stable. Okay? So we got to go through and categorize these as either mono, di, tri, or tetra-substituted so we can figure out which one's going to be our more stable molecule, aka our major product at high temperatures. All right, this first one here, what is this one? Mono, di, tri, tetra. We're going to look at these two sp2 hybridized carbons, and we're going to count how many carbons are bound. We just have that one, so this one's mono-substituted. What about this one over here? We look at our sp2 hybridized carbons. We're going to count how many carbons are bound. We got 2 of them, so this one's di-substituted. What about this one? This one's tri-substituted. All right, we look, we have 1, 2, 3 carbons bound. And the last one, 1, 2, 3 carbons bound, also tri-substituted. So mono, di, tri, which one's the more stable molecule here? Tri. The one that's the higher degree of substitution. In this case, we got a tie. So these two products we would expect to be produced in the same amount. We would call them both our major product of this reaction. All right, so we drew all 4 possible products to determine which one was the most stable. All right. Cool. All right, we're going to move on here. Our next chapter. Chapter 15 is on what's called aromaticity. And we're going to have to lay some groundwork before we can actually address what it means to be aromatic, what aromaticity is, all right? But what we're going to see is this chapter focuses very heavily on a molecule that's quite famous in organic chemistry, what's called benzene. All right, does everybody know what I mean by benzene? Okay, benzene's kind of this famous molecule. I'm sure you've seen it before. It's a 6-membered ring. Where every other bond is a carbon-carbon double bond. All right, so benzene was first discovered like early 1800s, pretty ancient chemistry going on at this point, all right? And it was a bit of a puzzler to early scientists. One thing that they were able to do pretty early on was determine the chemical formula for these molecules, right? So they knew that this molecule was C6H6. And they even had a sense that it was this ring with these double bonds in there. Kind of the only way that you can draw it that makes much sense. All right, but this is kind of where everything got to be confusing to early scientists, because what do we know about the length of double bonds compared to single bonds? Double bonds are what? Longer or shorter than single bonds? They're shorter than single bonds. So if I were going to do a molecule that's this ring structure where every other bond is a double bond, and I'm going to make this kind of dramatic here, we would expect it to have these long single bonds and these very short double bonds. All right, so this is what they expected here. Long carbon-carbon single bonds and short carbon-carbon double bonds, leading to this sort of a structure here. All right? But there was also early experimental evidence that suggested that that wasn't the case, that all of those bonds were actually equal length, much like how I drew it over here to begin with. All right? We have this like very perfectly symmetrical structure here for our benzene ring. So why is it that this structure with our short double bonds and our long single bonds is correct, and instead they're actually all the same length? All right. Well, we kind of already knew this because in this course we've already introduced this idea Benzene has this spacing of the double and single bonds that we called what last chapter? Where we go double bond, single bond, double bond. What do we call that? Conjugated, right? And so benzene has these pi bonds. These pi bonds all got that perfect spacing to where they're all conjugated with one another, right? And remember what that means. Each one of these has these p orbitals, and these p orbitals are overlapping to form that pi bond. But now all of your neighboring carbons have those p orbitals. They've all got those pair of electrons forming those pi bonds. And instead of remaining in place, those electrons are going to delocalize into those other p orbitals. All right, so just like before with our conjugated pi bonds, these conjugated pi bonds mean that the electrons are delocalizing around that ring. All right, so we have conjugated pi bonds, implying our electrons are delocalized around that ring. All right, so then why am I allowed to draw benzene with this nice symmetric structure here? Well, really, if I was being really good, I would include my other resonance contributor, which is where those double bonds have now traded positions with one another. So these move over here, these over here, and these over here. All right, so if I do my other resonance structure, we see why all these bonds are the same length, because those electrons have spread themselves out to be in both of those positions at once. Okay, so benzene, famous molecule because when it was discovered it was kind of a puzzler as to how it was behaving, and it led to this theory of conjugated pi bonds, this idea of resonance and delocalization of electrons is something that we already introduced earlier in the course, but from the scientific standpoint, from the history of chemistry, it was really benzene that helped bring these ideas up front because it exemplified all of that so strongly. Okay? You will sometimes see benzene drawn as that six-membered ring, and instead of having those pi bonds explicitly drawn, you see something like this dotted line circle in the middle. That's to indicate that those electrons aren't remaining in place, but are delocalized around that ring. Okay, we don't use this. You won't see this when we're doing our mechanisms or our chemical equations and stuff like that. We don't like this because it doesn't keep track of a number of electrons correctly. Nonetheless, I think it's a good mental picture to have in mind that those electrons in that ring are delocalized around that entire ring. Okay, but we're not going to see it like this. You'll see it outside of chemistry like that a lot. All right, the other thing that was puzzling to them is what do we know about these conjugated pi bonds? Does that make the molecule less stable or more stable? More stable, right? And that was another thing that was really confusing about benzene. Is benzene, despite having all these carbon-carbon double bonds, does not behave the same as alkenes, right? So we kind of put it in its own special category. We're going to talk about reactions of benzene, and we're going to see they're very different than reactions of other carbon-carbon double bonds, right? Because instead of just having a carbon-carbon double bond, you have this fully conjugated ring here of pi bonds. So this thing behaves, it's its own beast. All right, cool. So we're going to start this chapter talking about how we name these benzene derivatives, nomenclature of benzene derivatives. Grab a ring here. So if we just had this ring all by itself, that would be benzene, all right? If we start putting substituents on there, making what we call benzene derivatives, how do we name this thing? Okay, so step one, as always, we need to find our parent chain. All right, our parent chain is that benzene ring. And we name it benzene. All right, so if I'm looking at this molecule here and my first step is to identify the parent chain, that parent chain is that 6-membered benzene ring. All right, I'm going to leave a little bit more room here under parent chain because we're going to complicate things here in a little bit. All right, but moving on, next step is our substituents, finding and naming our substituents. And there's nothing new to add there. In this case, just like always, this 3-carbon substituent here would be called what group? A propyl group. All right, but now we're going to get to our numbering of our parent chain. And this is where things get a little weird for benzene. All right, so first of all, this example would be a mono-substituted benzene ring. There's only one substituent on there. And so if we're going to number this carbon with our propyl substituent on it, what number are we going to give it? 1. If we moved our propyl group over here, what number would we give it? 1. No matter where you put that propyl group, it's always going to be on carbon 1. So just like we saw with our cyclic alkanes, for our mono-substituted benzene rings, we don't include the locant in the name. It's always just going to be carbon 1. So this thing right here would just simply be propyl benzene. Right, so for mono-substituted benzenes, we do not include the locant in the name. All right, I'm going to leave a bunch of room here because this is where we're going to complicate things. The last step is to just put that name together. And again, we got nothing new to add here. All right, so if we have a benzene derivative, that benzene ring is going to become our parent chain. If it's a mono-substituted benzene ring, we're going to omit the locant of that substituent. All right, so then everybody's going to take a second and name this example for me. My parent chain is that benzene ring. We have a bromo group on that benzene ring, so this would be bromobenzene. All right. Cool. So now, what if we have more than one substituent? Specifically, we're going to look at di-substituted benzenes. And this, we're going to use this designation that's very unique to benzene rings. We're going to use what we call the ortho, meta, or para designations. All All right, so there's this terminology that's unique to benzene rings, specifically to di-substituted benzene rings, and that is using this ortho, meta, or para designation. All right, so what the heck do I mean by that? Okay, so I'm going to take my benzene ring here, but now I'm going to add two substituents on there. All right, and importantly, if I put those two chloro groups right next to each other, I would have a distinct molecule than if I left one carbon in between them. All right, so these are two distinct molecules. They got different chemical and physical properties, so we need to make sure to name them differently. All right, we're going to use this ortho, meta, or para to indicate our spacing of our two substituents. If your two substituents are right next door to one another, this is what we call the ortho isomer. So the correct name for this molecule here would include that ortho designation or be ortho dichlorobenzene. All right, you can get lazy and shorten that to just simply O dichlorobenzene. That's perfectly acceptable as well. All right, but when they're right next door to one another, that is what we call our ortho isomer. If they've got this one carbon in between them, this is our meta isomer. All right, so the correct name of this molecule would be meta dichlorobenzene. Or just simply M dichlorobenzene. All right, and then lastly, if these two substituents were located on opposite sides of the ring from one another, all right, on opposite sides of the ring, this is our para isomer. So this would be para dichlorobenzene or P dichlorobenzene. All right, so we have this unique system for benzenes to indicate the spacing of two substituents. When they're right next door to one another, we call those ortho. When they're one removed from one another, we call those meta. And when they're on opposite sides of the ring, those are the para isomer. All right, so how are we going to keep these positions, keep track of these positions in our brain? All right, well, let's say that our first substituent is located here. Again, right next door are those ortho positions. Next down are our meta positions. And then on the opposite side are our para positions. And again, sometimes remembering the dumbest little thing will help it stick into your brain. So just notice our order here is O, M, P. Say it to yourself like OMG, but OMP. All right, that is the order of our three different designations, ortho, meta, and para. All right, so then you're going to do this example for me here. parent chain is that benzene ring. These two substituents here are 2 carbons long, so these are ethyl groups. And these 2 ethyl groups are located what? Ortho, meta, or para from one another? Meta. So this would be meta diethyl benzene. Okay? There is an exception to, oh look, I don't make the rules for nomenclature here, I'm just relaying messages, all right? But there is an exception to ortho meta para. And that is when you have non-identical substituents. All right, so if, for example, we had a benzene ring where one of those substituents was an ethyl group and the other one was a chloro group, we would not use ortho, meta, or para. Instead, we just use our normal numbering. So we would treat this just like we would if it was a cyclohexane ring, where we're going to number around that ring. And again, our goal, as always, is to include the lowest possible numbers in the name. All right, in this case, I actually got 2 different ways to number. 1, 2, 3, 4. Or 1, 2, 3, 4. And in both cases, I got a tie. I got a 1 and a 4. So how do I break my tie? Alphabetical order, right? So in this case here, we would have to go with the red numbering scheme. Yo, keep it down a little bit. All right. We would have our chlorine on carbon 1, 1 chloro, 4 ethyl benzene. All right, so we use this ortho meta para designation unless we have these 2 substituents that are non-identical, that are not the same thing. Then we just use our normal numbering. All right, we'll also use our normal numbering if we have more than 2 substituents. So any tri-substituted or more, that's when we also use our normal numbering. All right, so take a second. Whoops, not that. All right. Okay, so if we had something like this where now we have 3 chloro groups on there, our whole ortho meta para thing breaks down. All right, we can't use ortho meta para because ortho meta para specifically tells us the spacing of 2. So if we got 3 of them on there, we're just going to have to number our ring. And again, your goal is to put the smallest possible numbers in that name. So everybody take a second and name this trichlorobenzene for me. So if we're going to build those lowest possible numbers into our name here, this would be 1, 2, 4 trichlorobenzene. All right, so when we have these benzene derivatives, our parent chain is that benzene ring. And depending on how many substituents we have, we use a different strategy for indicating the position of those substituents. If there's one, we don't worry about it. Right? It's always going to be on carbon 1, so we don't have to include the locant in the name. If there's two of them, we're going to use that ortho-meta pair designations. And if there's 3 or more, that's when we go to our numbering. All right, I said we were going to leave some room up here to complicate this parent chain business. Okay, and that is because there are a few benzene derivatives that are special benzene derivatives. These special benzene derivatives have these names that have just stuck for historical reasons, and so we refer to these molecules by their special names. All right, some of them make a lot of sense. Other ones seem to have come out of left field. All right, so first of all, our first one is if we stick a carboxylic acid group on that benzene ring. This molecule here has its own special name. This is benzoic acid. If we put an aldehyde group on that benzene ring, this is benzaldehyde. All right, and then lastly, or rather, next one here, we put an alcohol group, a hydroxyl group on that ring, benzaldehyde. Sorry, that got deleted somehow. All right, this molecule has its own special name. This molecule is phenol. Which is a little weird, but it does still have that OL ending that we associate with alcohols. All right, so kind of an easy one to keep track of. So benzoic acid has that carboxylic acid group, benzaldehyde has that aldehyde group, and phenol has that alcohol group. All right, there are 2 more that kind of come out of left field here. If we stick an amine on that benzene ring, this is aniline. And if we make a methyl ether off of that benzene ring, this is what we call anisole. All right, so the top 3 have names that really hint at their functional groups. The bottom 2 just seem to come out of left field here. All right, when we have our amine, it's aniline. When we have our ether, it's anisole. There is a little trick that we can use to keep these straight, right? They're very similar sounding names, aniline and anisole. What we can notice is that aniline with the N has that nitrogen, and anisole with the O has that oxygen. All right, so just a little trick to try to keep these very similar sounding words straight. They refer to these 2 distinct molecules. Aniline is where we have that amine group with the nitrogen. Anisole is where we have that oxygen, that ether group. So these are these special benzene derivatives. These molecules, they have their own special names. And so what happens if we make a derivative? We start adding substituents to one of these molecules here. Importantly, these special benzene derivatives, what makes them so special is that they become the parent chain in our molecule. So let's take one of those parent chain, or rather one of those special benzene derivatives. I'm going to put a substituent on there. All right, importantly, when we look at this molecule, because it's got that functional group indicating it's one of those special benzene derivatives, not only is the ring my parent chain, but also that OH group up there, my parent chain here is now phenol. Right, that special benzene derivative is present, so that's going to become the parent chain in my molecule. We have this bromo group on here, and you're going to finish off naming this molecule by including that ortho-meta-para designation to indicate the spacing of those two groups. What's up?
What if we had two different functional groups? How do we separate?
Don't worry about it.
Okay.
We're not going to get there. So we're not going to mix up. I mean, that's a good question. There's certainly a way to do it or whatever. It's probably got its own weird name, but you don't have to worry about us smashing two of these together or something like that. I'm going to pick my battles here. All right, so which one is this? Ortho, meta, or para apart? So this would be ortho bromophenol. Or just O-bromophenol. What's up?
I thought if the substituents were like non-identical, then it...
Great question, okay? There's this very weird subtle designation that we make in nomenclature between substituents and functional groups. So these are not two substituents. One of them's a substituent, the other one is the functional group on there, which is why it's the parent chain. So a substituent would specifically be alkyl groups or those halogens, the things you put out front of the name, not the things we build into the back half of the name. So, and I guess bottom line, kind of short answer, if it's one of these special benzene derivatives here and some other substituent, we use those ortho-meta-para designations, right? These are now our parent chain. We treat these as functional groups, not substituents. Okay, lastly, so wait, let's just real quick go back and update our rules here. Our parent chain is our benzene ring. We use benzene, or it's our special benzene derivatives. What's up?
We had another bromo group on that problem we just did.
Yep.
Would you use the numbering?
You'd have to, yep. As soon as you got three things on there, you got to use the numbering. All right, so last thing we're going to cover here, our last category, we got some other benzene derivatives, but these are the not so special ones. these not so special benzene derivatives are molecules where we're going to use their common names, but they do not become the parent chain in a molecule. So these are ones that you need to be able to recognize as having their own unique name. You don't have to worry about us starting to decorate it and then keeping that as the parent chain in the molecule. All right, the first example would be methylbenzene. We don't call it methylbenzene, it's got its own special name. This is toluene. All right, and then dimethylbenzene. We don't call dimethylbenzene, it's also got a special name. It's one of the cooler ones. This is xylene. All right, and this is actually a particular isomer of xylene here. Which xylene is this? Ortho, meta, or para? So this is the paraxylene. All right, so these are ones that I expect you to be able to recognize: methylbenzene as toluene and dimethylbenzene as xylene. All right, but you don't have to worry about the whole of them becoming a parent chain business. Truthfully, there are instances where you do see toluene as a parent chain and then other ones where there aren't, and it's just kind of a confusing landmine of exceptions, and I'm going to pick my battles and not worry about all that. All right, so point being you need to be able to recognize this rather as toluene. You don't have to worry about if we stick other groups on there, keeping that as the parent chain. Cool. All right, so let's just do a few more examples here. So for this first one here, not only is that benzene ring, but also this carboxylic acid functional group. This is all my parent chain in this molecule. So my parent chain here is one of those special names, our benzoic acid. I have this 2-carbon ethyl group. And I'm going to indicate the spacing of those two using what? Meta. So this would be meta-ethyl benzoic acid. All right, for this next example here, what is it? Ortho, meta, para, trick question. Yeah, so we can't use it, right? We got 3 things on that ring. Ortho, meta, para doesn't work anymore. So we're going to have to number our ring, okay? Now, importantly, I wanted to do this example specifically because when we number our ring, remember, this ring has this special amine group on there, which makes it its own parent chain aniline. So importantly, when we number our ring, our functional group is always sitting on carbon 1. All right, the presence of that special group there designates what carbon 1 is when we number our ring. All right, from there, whether we're going to go clockwise or counterclockwise is going to depend on whether is going to be because we want to include the lowest number in the name. So I'm going to go this direction. But importantly, that special functional group always sits on carbon 1. So let's just note that special functional group is always carbon 1. So when we name this molecule here, this would be 2,3-difluoro. Since that parent chain, that aniline, is always on carbon 1, I don't bother including the 1 in the name. I just say 2,3-difluoroaniline. Okay, that special functional group is always on carbon 1. So I don't have to say it's 1 aniline. I know it's 1 aniline. I'm just going to indicate the location of those 2 fluoro groups. Cool. All right, we got all our nomenclature out of the way here. We will pick up next time discussing this aromaticity business.